Okay, so let's have a look at this example here. So we've got this pair of gears. We have a moment that is being applied here, a torque, and then it connects to this gear here, and then that gear connects to another gear here, and then it connects to some box. The box is supplying the energy or using the energy transmitted, one or the other. From a statics perspective, it doesn't really matter at this point, whether or not it's using it or not. So again, I just redrew this here. The x-axis this way, y-axis this way. So again, x-axis this way. That'll mean that based upon our right-hand rule, that there is a positive moment that we're applying to this shaft. So positive moment about the x-axis. So we need to kind of figure out how those moments relate to one another. So we got the gears here, they mesh, the teeth mesh there. So we can just kind of draw a quick free body diagram of the gear at C. It's this one here, C. So it's going to have a moment applied to it. Again, a positive moment about the x-axis applied to it by the shaft. And then it is going to also have a force applied to it from the other gear. So it's going to want to be turning this way, and the other gear is going to be like, well, okay, but if you do that, I'm going to push you back. So as it pushes it this way, as it pushes the other gear this way, the other gear is going to push back at it this way. Good old Newton's third law. So we can figure out what the magnitude of that force is just by taking the sum of our moments. So the sum of our moments is going to be the positive 900 Newton meters minus F times the 40 millimeters that is the radius of our gear here. Based upon that, quick rearrangement of the equation, and we can solve for F. And F's just going to be the 900 Newton meters divided by our 0.04 meters. Again, I converted to meters there just to be able to cancel that out easily and then be left with newtons. And then we got a relatively large number, so I put it in terms of kilonewtons. So 22.5 kilonewtons. So again, free body diagram of the other gear. We got this 22.5 kilonewton force that's being applied to it by this gear. When this gear wants to turn, it's going to push this way. If it's being pushed that way, then we're also going to get a reaction from the other gear. So the torque reaction. We're also going to get a force reaction from the other gear. It's from the shaft. No, not the other gear. We're going to get a force reaction from the shaft. I'm not going to bother showing that because this is a torque question and not necessarily a bending moment question. We'll be getting into those later. But for now, we're worried about what happens with the torque. We weren't asked about any of the other reactions. So just looking at the stuff that causes moments right now, there is other forces involved, but for now we're not going to be worried about them. So we got this torque going on here. That's the torque that's going to be applied to the gear B by the shaft AB. So again, sum of the moments is 0. I got that this negative moment here because that's clockwise, which means that this needs to be counterclockwise. So it's 20. Solving for that gives us 2.25 kilonewton meters or 2,250 newton meters, depending on how you want it. So again, keeping in mind our directionality, that is a positive moment that is applied to the gear from the shaft. We invoke Newton's third law. That also means that the gear itself is giving the shaft an equal and opposite reaction. So the moment that's being applied to the shaft is going to be a negative moment instead of a positive moment, which jives with what we should expect to happen. If we got an input coming around here that's going like this, then we expect an output to be going the opposite way because it goes through one set of gears. Flips direction every time you go through one set of gears. So directionality is important. Try to keep that in mind. And then we go to the stresses. So we've got the for the section CD here, the top the one with the smaller gear on it. We know that the tau max is equal to the torque times C divided by J. And again, they use C instead of R because C is like the distance from the center to the point you're looking at, which for all circular shafts is just going to be the radius. That having been said, this formula does work for non-circular shafts, so it is what it is. Anyway, so the J for a solid circular shaft is, or the J for a circular cross section is pi over 2 times C to the fourth, or R to the fourth, whatever you want to plug in there. Whichever you want to denote it as. And then just plugging this into here means we got move the 2 on the top, we got the pi on the bottom, we got the C to the fourth on the bottom, and then the C on the top. So those cancel out, or at least one of those cancels out. We got a C over 3 here. That means that our tau max, if we want to put it in terms of radius as well, can be given as that. And this is me forgetting to calculate it in terms of radius. I plugged in the diameter instead, so again, you'll double check your work after. But we have plugging in our values gives us so 2 times 900 Newton meters divided by pi, and the 0.045 meters divided by 2. So again, the diameter of this shaft was given as 45 millimeters. So getting the I put that in terms of meters so that things cancel out nicely, and of course we need to remember to divide by 2 because we want the radius, not the diameter. So put it in terms of meters, so stuff cancels out. So we can cancel out this meter here, and that gives us. This means that whatever we calculate here is going to be in terms of newtons per meter squared. So PA, that ended up being an inconveniently large number, so I converted that to 50.3 megapascals. And then for AB, so this section here, 2 times the torque divided by pi times the radius in meters cubed. So the radius there is 60 millimeters, so 0.03 meters would be the radius. Sorry, diameter there was 60 millimeters. 0.03 meters would be the radius in meters, and that just gives us 53.1 megapascals. So yeah, again, traps to avoid. Try make sure that you're using radius, not diameter. I know that happens a lot, but and I never claim to never make any mistakes when working these examples either. But that's one to watch out for. All right, see ya.